Hello, everyone, and welcome to the Switch Statement Podcast. It's a podcast for investigations into miscellaneous tech topics.
This is our third episode on Gödel, Escher, Bach by Douglas Hofstadter.
Hey, John, how are you doing?
Hey, Matt, how are you?
I am doing all right.
Are you infuriated by this Mew puzzle?
I am just seething right now because I think we were misled.
We were trolled.
He trolled us.
70s Hofstadter trolled us in 2024.
Yeah, dude, and will long into the future. So what we're talking about is the Mew puzzle. This is the name of this chapter. I think he does a good job here easing us into the world of formal systems.
Yes. Yeah.
So the whole point of this chapter is to lay out this very small universe, almost like the minimal universe where there is an interesting question you can ask about it. And he calls that the Mew puzzle.
And he kicks off the chapter. So I guess this will be the thing in this book where he'll have these like, what do they call them? What does he call them? The dialogues or something. He has a word for them, which I don't want to look up right now, but he kicks off each chapter with kind of this weird parable type thing. And this one was kind of I don't know if I want to use the word funny version of Zeno's paradox.
Yeah.
It was like this dialogue between Achilles and the tortoise. And they were talking about doing a race. And there's a thing called Zeno's paradox where if you keep moving halfway to a point, you will never get there. It's kind of a paradox that disproves that motion is even possible.
Right.
Which I feel like is very, on brand for this book, like kind of disproving things that are clearly real by twisting words around.
Do you know the resolution to Zeno's paradox?
The resolution that like makes it false?
Well, because clearly, the thing that makes Zeno's paradox a paradox is that clearly things move.
Right.
So basically, I think what Zeno's paradox says is, Achilles and the tortoise are racing, right? So the tortoise starts off with a head start. Once Achilles runs to where the tortoise was, the tortoise will have moved.
Right.
And then you can do that again and do that again, but the tortoise is always going to be ahead of Achilles, because you can keep on doing that, ad infinitum.
Which is completely absurd.
But clearly in the real world, eventually Achilles will pass the tortoise. So it's what's the resolution to the paradox? And so I guess my question is, have you heard, I didn't figure this out myself. I watched a number file video about it, but.
Oh, I see what you're asking. There's actually a mathematical disproof or something.
Well, there's an explanation of the phenomenon. Because
no, I'm not aware of this.
Okay.
I just thought it was one of those things that was clearly not true.
It's funny because nothing in the presentation of Zeno's paradox is false. It's just misrepresentative. So The resolution of the paradox is that, yes, if you keep on doing those additions, Achilles will never pass it. But those time steps become infinitesimally small to the point where the amount of time converges towards a finite amount. So basically that series only ever will sum up to be the point where they cross. But it's only a small, the trick that the paradox plays on your mind is you kind of imagine each one of these time steps as being roughly equal in time. So eventually if you add if you add them all up, it'll be infinitely long in time.
Yeah.
And they'll never cross. But the point is the distance is bounded and the time is bounded of that summation. So it's just not modeling anything past the time or the space of Achilles crossing the tortoise.
Yeah.
Does that make sense?
I think it makes sense. I think this is going to be an issue for me with this book where I was never one to really explore these types of Like, I almost think of these as like nonsensical word puzzles where you're just, you're describing something in a way that kind of breaks reality. And I've the way my brain has always worked is like reality is reality, and sure, you can like describe it in any way, some of which might break reality, but you can't actually break reality with words.
Exactly.
And I feel like I have this thing where my brain just kind of like turns off when this type of thing is being discussed. I think I'm just
You're breaking out of the system, it sounds like.
yeah, maybe I'm breaking out of the system. He started the chapter, and I really perked up because he basically introduced formal systems, which you and I have spent most of our lives dealing with formal systems.
It's so funny that you say that because any programmer who has learned about like searching or has taken a class in algorithms, like they will feel very at home because it feels like I'm just like, okay, this is another algorithms problem, or I'm like searching through a graph, or
Yeah. It's funny because in this chapter there were so many things that my brain is like so trained to just immediately internalize. Like he mentions the rules of this mu system, and immediately my brain is like, okay, these are the rules, and it will perform the calculations and not keep the rules intact. But then there were things in this chapter that my brain is not trained to do. Mm-hmm. And I was like, oh, this is very cool. Like, I hope he goes into more detail on this, because like this is a skill that I would like to have. And anyway, maybe we just start jumping in and describing what the mu system is.
Yeah, let's talk about it. So the mu puzzle is fundamentally it's a string manipulation puzzle. Mm-hmm. So you start with a string of letters, and then you are given a series of rules about how you can modify those letters, sometimes under certain circumstances. So basically they say, okay, well, if you start with the string mi, is it possible to, with, just by rigorously applying the rules, to wind up with the string mu? So that's kind of like the way the puzzle is proposed.
And do you have the rules in front of you by any chance? I didn't write them down in my notes.
Yeah, I have them here. So I can just go through them quickly. So rule 1 is if your string ends in an I, you are allowed to add a U at the end of it. So that one's pretty straightforward.
So if you start with MI, you can convert that to MIU.
Boom, MIU, yeah. So if you have the string MX, and now we should say the only literal letters you're actually allowed to have in your string is M, I, and U. So if you have the string MX, you're allowed to produce the string MXX.
Yeah, and X represents everything after M. So
exactly.
if you have MI, you can create MII. But then you can create MIIII, because you basically have to repeat everything after the M.
So I think of this as just like the doubling rule. So like, you have the M, and then you could just like double everything after the M. And now rule 3 is if you have III in your string, you can turn that III into a U.
Right. So if you start with MI, you can create MII, then you can create MIIII, and then you can convert any of those blocks of 3 I's into a U. So you can create MIU or MUI.
And we already generated MIU, right? Through another route, right?
Yes.
Last rule, pretty straightforward. If you have UU, 2 consecutive U's, you're allowed to squish them down into nothing. You can just obliterate those U's.
Right. Yeah, so those are the rules of the mu system. He then goes on to just explain more broadly, like formal systems, and he discusses theorems, axioms, and rules. where a theorem is any string producible in a system. So we just gave a bunch of examples like MIU, MUI, MII, all those. Axioms are free theorems. So basically when you're like introducing the system, like the mu system, you sometimes also introduce these like starting theorems. Like in the mu system, the starting theorem is MI. But then the rules are just those things that you just described. It's basically like how you can take existing theorems and produce new theorems. And there's two types of rules. There's rules of production and rules of inference. And I guess rules of production are where you're just adding stuff to theorems, right? Like converting MI to MII. What's a rule of inference?
I don't think that the mu system has any rules of inference. A rule of inference may be like a conditional rule where it's like, if you have this, then you have that. I don't think we have any of those rules here.
Okay, yeah. I mean, the mu system is like kind of this dead simple formal system, so it probably lacks a lot of these sophisticated things.
One of the things that I didn't like, it sounds like a theorem. Like, I guess in my kind of casual brain, I think of a theorem as something that may or may not be true. But it sounds like in this, like a theorem is true. It's something that has been logically derived from something else. So should I treat a theorem as true?
Well, it's interesting because I think we hear the word theorem in math and we think to ourselves, like, we don't know if that's true or not. Or, you know, there's some theorems that everyone thinks are true, but they haven't been like definitively proven to be true. And I took it after reading this as, you know, brilliant mathematicians are sort of using their intuition to produce these theorems that they think will eventually be derivable in some formal system, but they're not sure. You know what I mean? So it actually does fall, you know, he says a string producible in a formal system. You know, math itself is a formal system. And theorems in math are strings that can be produced in that formal system. But I think a lot of these theorems that we don't know are true or not, they're almost like guesses. You know, it's like some mathematician is guessing that this is the theorem.
So is this as if you came up with a string? I'm like, hey, John, like I just discovered MUIIUIUIIIUI. Like this is my theorem. Like,
exactly.
That's kind of the essence of my question here. It's not a capitalized essence, but it's just a regular old essence. But of my question is that string of MIs, M and U's and I's a theorem? Or does it only become a theorem once I've found it through like a systematic search of this space?
Yeah, I mean, he does say this is a string producible in a formal system. So by that definition, I would think it would only truly be a theorem once it's proven to be able to be produced. But I do think that in math, like parlance or whatever, there are many theorems that we like don't know are definitively proven, but we think are true. And I wish I had some examples, actually.
Pythagorean theorem, right?
Pythagorean theorem.
He actually says this, actually. A theorem, capital T, is a statement in ordinary language which somebody once proved to be true by some sort of logical argument.
Oh, right.
Which
yeah,
is
he did have
crazy
that section.
Because I guess I always thought theorem, like, I think of theorem and theory as like kind of similar, but I guess a theory is also much more rigorous than people use it generally.
Yeah.
You know, in common parlance. But anyway, so a theorem is something that, according to some formal system, we kind of know to be true.
Yeah, but aren't there some theorems that we're like not 100% sure are true?
Well, aren't those called like conjectures?
Maybe.
Because there's that like the Bach conjecture, right?
Yeah. Okay, but anyway, so he goes on. So the whole topic of this chapter is this mu formal system and the mu puzzle, which is can you start with can you start with MI and eventually produce MU by using all of those rules that you just mentioned. And both of us, you know, what the way this podcast works is we both privately read the chapter and then we just meet, you know, on a day and like discuss the chapter. We don't have any pre-planning. It's very kind of shot from the hip.
Right.
But both of us wrote programs to try to brute force solve this puzzle.
I spent more time than I would like to admit just going through as many of these as I had these completely disorganized arrays of like strings and like arrows and what have you, and I very quickly ran out of space. I went back and I realized that he didn't phrase it in such a way that actually tipped his hand as to whether or not it was possible. But he says, can you produce mu?
Mm-hmm.
And I think it's not quite as bad as like, how do you produce mu? Because that would indicate to me that there is a way.
It's possible, yeah.
But can you produce mu? I feel like it's kind of a gray area because there's an interpretation where it's like, oh, like, can you get me a glass of water? And then you find out that the glass of water is at the end of infinity.
So this is why I am infuriated, because I wrote this terrible brute force algorithm, which, by the way, I have a couple of factoids about the mu puzzle.
Oh.
Well, I guess just one interesting factoid. I'm not going to bury the lead. On the 11th iteration of the brute force version of the mu puzzle, there are 28 million different theorems that have been produced. So and what I mean by the 11th iteration, because we haven't discussed decision trees yet, but what I mean by the 11th iteration is like you start with MI, and from MI you can produce MIU, like we said earlier, and you can produce MII, and I think that's it, right? It's just
I think
those
so,
two.
yeah.
But then from those two, you can then produce MIUIU, right?
Mm-hmm.
I'm going to screw this up. And yeah, what else?
MIIII.
Oh, right. Yeah, because MII can become MIIII.
But that's it too. Like both that, there's only one I think from each of those, which is the double. You can always apply the doubling rule.
Right, and then there's also MIIU, right? Because MII ends in an I, so you can add a U to it.
Oh, right. Yeah, that's a good call.
So you can think of it like a tree. That's why they call them decision trees, where the apex of the tree, like the star on the Christmas tree, is MI. And then you have a row of two, MII and MIU, and then you have a row of three. On the 11th row of that Christmas tree, you have 28 million nodes, which is why I let this program run for like 15 minutes, and then I just turned it off and decided it was impossible to produce MU.
Right. Yeah, I did a very similar thing. I didn't do it quite as rigorously in terms of defining layers of a tree, but I just said, okay, once you generate 100,000 of these things, like just bail. He hasn't tipped his hand, but I am of the opinion that it is not possible to produce MU in this system.
Yeah, I agree too. He said he would give the answer, but he has not given the answer yet. So we remain in suspense, and I guess we'll let the listener know later whether this is possible or not.
So what is Douglas Hofstadter trying to teach us with the mu puzzle?
That's a good question. I mean, I think for one thing, he's just trying to introduce this notion of a formal system. But I think he's trying to do something more interesting too, which is like learning how to move through a formal system by using these rules. And we will probably use the example of programming nonstop because that's what we do.
Yeah.
With programming, you're in a formal system. Like you can only write certain combinations of words and characters. And throughout your programming career, you get better and better at navigating this formal system and representing these more and more sophisticated things. When you get old, you start getting worse at it. That's kind of where I'm at. But it's kind of this amazing skill to be able to take these rigorous rules and use them to bend the universe to your will. And that's kind of what mathematicians do. It's what physicists do. And it's sort of what programmers do to a certain extent.
He uses this as an example to draw a distinction between a machine and a human. And it's funny because in your example, you're talking about how for a human, it's an achievement for them to be able to work in the formal system.
Yeah.
But he almost is more like, well, the cooler thing about humans is that they can't not like consider outside of the system. Like they can't not think of or learn things that aren't explicitly stated in the rules of the system.
Yeah, yeah, and it's almost difficult for a human to like fully be in a formal system, whereas a computer is like by definition like stuck in a formal system. And
Right.
it's only in very super recent history that we have developed computational systems that sort of feel like they're not locked in a formal system,
Right.
even though they really are when you really break it down. And now it's becoming this interesting, philosophical debate of like what even is intelligence.
Yeah. Is it breaking out of the system or not? Speaking of which, one really minor point about like LLMs or what have you is when I use Copilot. It's this thing from GitHub that like tries to autocomplete your code with an LLM. When I started to write this, I wrote like mu rules. Boom. It misremembered them, but it knew exactly what I was doing. So it created like a rough approximation of of the rules when I went to write the program out, which was like wild to me.
Crazy.
So
Yeah, actually, that's super interesting that you mentioned that because there was a tidbit in the chapter where he mentioned that humans have this weird ability to kind of have insights about a system,
yeah.
whereas computers can't have insights about anything, or at least they didn't used to be able to do that back in the 70s when he was writing this book. But he mentions how a human will quickly realize that there is always going to be an M at the front of any theorem.
Right.
But a computer doesn't even have a concept of like realizing that there's an M at the beginning. Although I think if you asked GPT today, like if you fed GPT these rules into ChatGPT and was like, draw some insights from these set of rules, it would probably tell you that, there's always going to be an M at the front.
Yeah.
So I think there's going to be a lot of material in this book where he's, kind of mentioning the limitations of computers, and it's just not going to be true anymore at all. And it's kind of a testament to how far we've come.
I mean, he talks a little bit about M mode, U mode, I mode. This is like, it's funny because up until this point in the chapter, he's using M, I, and U as just these blank, like tokens that don't mean anything in themselves. But then he has this section where he talks about M mode, I mode, and U mode. And then he says M mode is the mechanical mode where you're operating kind of like a computer and you're just like mechanistically applying these rules without observing things.
Yeah.
And then there's I mode, which is intelligence mode, which is like now you're considering like things outside of the system. And then he teases this third mode, which is the un mode, the U mode. And he doesn't tell us he says it's the Zen way of approaching things.
Yes.
But he doesn't tell us what that means.
And I think this is sort of the way of thinking that I don't do this last, Zen mode or whatever. And I'm hoping that this book will sort of describe a mental framework for intuiting that it's impossible to produce mu, from the mu puzzle. Obviously, you can intuit that it's super easy to produce MII because you're literally just applying a single rule to the initial axiom.
Right.
But I think there's probably also this way of intuiting that, like, you can't produce MU. And I don't have that ability. Like, I still look at this puzzle and I can't definitively say whether it's possible or not. I can just write a brute force program and, like, believe that it's not possible. Well, you earlier mentioned exiting from a system, and he had a decent sized section about that. And I thought it was interesting because he sort of kicked the section off describing exiting from a formal system. Yeah. And then he sort of went on to describe like society itself. He was describing like, oh, we live in this that, and I can't remember. It's been a decent chunk of time since I read the chapter, but it was almost like he was describing, the sort of capitalist system that we live in. And then he went on to say some people break out of that system. And I don't know, it almost sounded like he was describing people who like go live off the grid or something and like write manifestos in a shed somewhere. One section I thought was funny was and this was actually part of exiting from a system, but he mentioned this Canadian chess program.
Yeah.
Like there was this long era where, they would have chess programs compete against humans and they would have chess programs compete against each other. These days, any crummy chess program can completely annihilate even the best human. Magnus Carlsen will get beaten 1,000 times out of 1,000 by even the most basic chess program.
Yeah.
But back in the day, grandmasters could beat chess programs. And he discusses this Canadian chess program that I guess would like resign early.
Yeah.
Like it would be in these positions that aren't necessarily losing positions, and it would just resign like almost midway through a game. And evidently that was, an interesting thing in the world of chess, like just this weird program that would exit from the system, be like, I'm done. I thought that was interesting. And then the last thing I have in my notes is just decision trees, which we described a little bit earlier, so maybe we don't have to rehash it. But decision trees are a super powerful thing. It's a thing that I actually learned in AI class. Like I took an AI class in college, and there's a very famous problem called missionaries and cannibals, which is where you start with 3 missionaries and 3 cannibals, and you're trying to get everyone to the other side of the river. In missionaries and cannibals, you can't ever have the cannibals outnumber the missionaries. And so, you basically do this thing where like, okay, I'm going to send 2 cannibals over, 1 cannibal back. Then I'll send a cannibal and a missionary. Well, but now the cannibals outnumber the missionaries on this side, so they eat the missionary. But anyway, the way that a problem like that can be solved is through these decision trees, where you basically just do every single possible thing in a huge tree, and then once you find a solution node, you kind of backtrack up the tree, and that's your path. And a lot of AIs use this. Chess AIs famously use this. They have tons of super sophisticated optimizations on this. But at their heart, they're still using this kind of, decision tree type algorithm. So just a very powerful kind of, if you're in software engineering, like this is a good tool to have in your tool chest.
It's funny because, in the case of the cannibal and the missionary, it's trivially discoverable, like whether or not each position is like still valid or not. Right.
Yeah.
I guess, let's say, I think one problem you run into chess is just the explosion of the space, right? It's just too large of a space to discover. But like,
right.
Is it the case that if you could explore the entire space of chess, you would always know which move to make?
Yeah, I mean, if it was feasible to generate every possible board within, the known time that the universe will exist, then yeah, I suppose you could just literally generate the entire tree of chess and just calculate the best possible move at any given moment. But like you're saying, I mean, you brought up a super interesting point, which is like missionaries and cannibals, it's trivial. It's like if number of cannibals greater than number of missionaries, bad. But in chess, that's extremely difficult to calculate. And it's called a heuristic function. It's basically the function that you run on each node in a decision tree to tell, if that node is good or bad. But in chess, you have a few signals, like you have material value, which is like the point value of all of your pieces. A queen is 9, a bishop is 3, a knight is 3, a rook is 5, that type of thing. But material value isn't everything, because you will often sacrifice pieces in order to do what's called a combination, where you do kind of this sequence of moves. So you'll be down material for several moves because you're doing this like forcing combination. And there's also these like tactics, like pins, where you basically, if you can attack the king through another piece, you're pinning that piece. Like that piece can't move because then the king would be in check. So that's called a pin. So in your heuristic function, you might give a pin some point value. So anyway, it's just, I think like you were alluding to, it's just, it's not just the decision tree that can get very sophisticated. It's like that heuristic algorithm itself.
Right. All right. Well, I think that was all that I had for the Mew puzzle. What about you? Did you have anything else?
Yeah, that exhausts my notes. But I will just end by saying, like, I'm pretty into this book. Like, the dialogue was super silly, and I was like, oh my God. But then the chapter started, and it was like, okay, you're talking my language, Douglas.
Yeah, this is feeling really like a computer science textbook. Definitely.
Yeah. Yeah.
Yeah.
I am going to get slightly smarter by reading this book, which is very exciting to me.
All right. Well, I will see you for the next chapter, John.